All right, so let me just first start by saying, what's left to do. So exam 5, the night class is doing that on Monday, 12/16 at 6 p.m. And the day class is doing it Friday, December 20th at 2 p.m. Both of these are in their usual rooms. So for the night class, that's S1326. For the day class, that's C1016. And the topics are first, conservation of linear momentum and conservation of energy. Then the stuff that we're going to talk about today, which is 2 sets of practice problems. That's rotational kinematics and rotational kinetics. And then it's also cumulative, so there'll be a couple of questions on old stuff too. And there will also be a lecture quiz. The rotational stuff that we're going to talk about today, kinematics and then kinetics, since we don't have as much time to do this stuff as I would like, the problems that are going to be on the test related to this are going to be closer, like more closer than usual to the practice problems. They'll just be sort of changing numbers around with the practice problems. So get comfortable with those, with the practice problems on these, and you'll be fine. And what? The quiz? No, that's cumulative.
The lecture quiz is cumulative.
Yes. Any other questions about the test? And then there's also problem set 2. You can hand that in, or you can put it in the, scan it and put it in the D2L Dropbox. And that's due by Friday, 12/20. So if you don't get it in by Friday, 12/20, then the best I can do for you is, give you a incomplete and then change your grade when you get it in. So that's an important day. Any questions about the problem set? And then I would appreciate it if you would look on D2L over the next couple days and just look at your problem set 1 grade and make sure that there's a grade there if there's supposed to be a grade there. So we can get that fixed. All right, and I think you should be able to see your total grade. I think it should be calculated on D2L and should be visible to you. So say it'll give you all the breakdown of the individual things and then say like 41% total, for any questions about, yes? That's right, I haven't. And so I will put something in the D2L news when I grade those so that you'll know, because otherwise, if it doesn't change, you don't know whether you just didn't get a higher score or what. So look in the D2L news and that'll tell you when I've graded the makeups. Oh, and then also for office hours next week, I put something on D2L about this. I'm planning to do essentially my same office hours as usual next week, except I was going to bump my my afternoon office hours on Monday and Wednesday from, usually they're from 4 to 6, and I was going to do them from 2 to 4. So if that's a problem, send me an email. And either, if it's a problem for people, probably I can work something out with people individually, or otherwise, I can just keep them the way they were. Okay, any questions? Yes? The makeup lab? Oh yeah, there is a makeup lab tonight, yeah. For some reason I was thinking makeup exam, like, no, you missed that one. Okay, yeah, makeup labs are tonight. Yes. Any other questions? Okay, so let's do rotational motion. So I'm going to start with kinematics. So rotational, you could also call it angular kinematics. And the deal is that until now in this class, we've treated objects as particles. Until now, everything's been particle motion. And that means that the objects, we've treated the objects as if they didn't have any length. And because they didn't have any length, we've also treated them as if there was no orientation. There's no difference to us what orientation an object is in. Now we are going to consider object orientation. And so this is the first time, if you think about it, it seems a little funny. It seems like an important thing. But in all of our calculations that we've done so far, even when we're talking about kids on carousels and airplanes and all this kind of stuff, the orientation of an object never came into anything. So when we talk about circular motion, we would talk about where in the circle a thing was, but we didn't make any distinction between whether the thing was facing this way or facing this way. We just thought about where on the circle it was, okay? And so now we're going to go from talking about circular motion as this, where the path is moving in a circle, to talking about changing orientations, rotations, where maybe the object isn't moving in a circle, but it's changing orientation. So this is the motion we're going to talk about now. Okay. But it's important to notice that there's a strong connection between rotational motion and circular motion. So rotational motion is strongly related to circular motion. And the reason for that is if you're dealing with an object that's rotating around a pivot point. So let's say you have a board, and the board is connected to, you know, a wall or something by a pin. So imagine this is a board that's free to rotate around this pin. Think of what individual points are going to do. So this is the pivot point. Then what's the motion that this point is going to follow as this object changes its orientation? It's going to go in a circular path around the pivot point. Okay? And an object out here is also going to go in a circular path. And that circle has the same center, but a different radius. Okay? So the relationship between circular motion and rotational motion is when objects change their orientation, material points on the object are in circular motion about the pivot point. And about the pivot point, I just mean the pivot point is the center of that circle. Okay? So, the rotational motion refers to the body as a whole, and the circular motion refers to individual points on the body. So as we start to talk about calculations with rotational motion, one thing that's going to make this all a lot easier is that the rotational motions that describe the motion of an entire body are analogous in a lot of different ways. Almost every single quantity that we deal with, every equation we'll deal with, has an analogous quantity or equation for particle motion, an analogous translational quantity or equation. So before I go into what these things mean, I just want to make a list of the translational quantity or equation and the associated rotational quantity or equation. So here are the rotational, translational analogs. Okay, so when we were first talking about particles, we started with particle kinematics. And what were the quantities that we dealt with in particle kinematics? Quantum tunneling? No. Yeah, right, exactly. So position, velocity, and acceleration. And with rotational kinematics, we're going to talk about this quantity, that's an angle theta, that I'm going to call the angular position. Omega, that's a lowercase Greek letter omega. It looks like a round W. And that's the angular velocity. And the Greek letter alpha, and that is, it looks like a goldfish, and that's the angular acceleration. And then when we were done with kinematics of particles, we went on to kinetics and introduced two more quantities. What were those? That's right, mass and force. So mass has a rotational analog that we denote with a capital I and a subscript. I'm using the subscript A for now. And that's called the mass moment of inertia. And that is a measurement of how easy or hard a thing is to get it rotating. An example of that is, in gymnastics, you get more points for doing a bunch of flips in a laid out position like this than you do if you tuck into a tight ball, because it's harder to get a laid out, long, stretched out object to rotate quickly than it is something that's tucked up tight. Obviously, the person's mass isn't any different in those two cases, but one's easier to rotate than the other, and that's sort of the idea of mass moment of inertia. And then the other one was force. And the rotational analog of force is, I'll call it M sub A. And you can think of that as the moment. People usually, as a shorthand, just call it moment, but so in parentheses, I'll put moment of a force about a point. And then the last thing that put these together was, well, there are a few equations actually. All those kinematic equations we'll see their rotational analogs for, but the one I want to get down here is Newton's second law says F equals ma. The rotational analog of that says the moment about A is equal to the moment of inertia about A times the angular acceleration. So notice, not only does it have a similar form to F equals ma, but this kinetic equation that we're going to for rotational motion even has all the analogous quantities in the same places. The rotational version of a force is the moment. Rotational version of the mass is the moment of inertia. The rotational version of acceleration is angular acceleration. Okay. And so if you always keep these analogous quantities and equations in mind, it's going to be easier to remember when to use them, how to use them. Any questions about that? All right. So when I talked about particle kinematics, I first defined position and then defined the other ones in terms of position. Remember, I started out, there was a picture of a train going over tracks, and we talked about how you had to define a 0 position, and then you could define the train's position. Once we did that, the velocity was a rate of change, like how quickly that position was changing. The acceleration was how quickly the velocity was changing. So I'm going to go through that same sort of approach here, but a little bit more quickly. So first, angular position. So the angular position holds for an entire rigid body. Not just a point on a rigid body, not just a single point. And to define this, choose a reference orientation for the chosen body. And imagine painting an arrow on the body in its reference orientation. So for example, if you're talking about the angular position of a car, you might choose sitting upright on its wheels as the reference orientation. You don't have to, but and so imagine just spray painting an arrow on the car in that position. Okay. Now in the car's chosen orientation, the arrow points in a new direction. And the angular position theta is the counterclockwise angle from the arrow in the reference position, or in the reference orientation, to the arrow in the chosen orientation. Okay, so to use that same example, now say the chosen orientation is this. Okay, what direction would that arrow be pointed now? You know, it's spray painted on there, so it moves when the car moves. So it's still going in this direction or something, right?
What does it say in theta is?
Counterclockwise.
Oh.
So the arrow in the reference orientation was this. The arrow in the chosen orientation, put the tails together, was this. So what's the angle here? 90, yep. So the angular position then is 90 degrees. But we don't represent these in degrees, we represent them in radians. And so since we're more used to thinking in degrees for angles, it's helpful to have a conversion. So to convert degrees to radians and back, just remember that pi radians is equal to 180 degrees. So if you have something that's, say that you have an angular position that's 61 degrees and you want to represent that in radians, you'd multiply by, 180 degrees goes on the bottom, pi radians goes on the top, the degrees cancel, and you get 1 point something 06 radians. SI units for angular position are radians. And radians are a funny kind of unit. You can think of them as being there, but really you can also think of it as just a pure number. So really it's not a unit. Just a pure number. So the angular position you could think of as 1.06 radians here, or you could just think of it as the number 1.06. One thing I want you to notice is translational quantities are different for every point on a body. For every point on a rigid body. Rotational quantities, on the other hand, have a single value that represents the entire rigid body. So if you look back at this car example, what's the translational, like what we've just called the position? What's the position of this car? Well, first we'd have to choose a zero position and choose an origin and coordinate system orientation. But once we did that, we still would have a problem, and that is that what part of the car do we want to know the position of? The car is 3 meters long or something. So the position of the rear bumper is different than the position of the front wheel, okay? But that's not true with angular position. When we got this angular position of 90 degrees, which ends up being pi over 2 when you convert it, that angular position represents the whole car. That's how the car as a whole is oriented from its reference orientation. Any questions about that? So then angular velocity remember that what we did to define velocity was we defined an average velocity as equal to the position at some later instant minus the position at some earlier instant divided by the elapsed time. And then we said to define the instantaneous velocity, that's just approximately equal to the same equation, just as that increment of time gets smaller. So for a small time interval, t2 minus t1, okay? And the way I'm going to define angular velocity just follows this exactly. So similarly, you could define an average angular acceleration that's equal to the angular position at some later instant minus the angular position at an earlier instant divided by the elapsed time. And then to define the instantaneous angular velocity, that's just an approximation of this same equation. As that time interval gets small. And this is the one that we're going to deal with, is instantaneous angular velocity. So based on this equation, what are the SI units of angular velocity? Well, what are the units of the numerator of this fraction? The denominator is seconds. The numerator is radians, or it's just a pure number. So angular velocity has units of radians per second, or if you keep in mind that radians are really not a unit, you can also think of it as just 1 over seconds. And so the angular velocity tells you how quickly the angular position is changing. Now, what about direction? Say that you have a positive angular velocity. Does that mean the object is rotating clockwise or counterclockwise? And how do you know? Counterclockwise. And how do you know that? That's exactly right. So you enter the angles as counterclockwise positive, and so that's exactly the same sign convention you have with angular velocity. And it's the same with angular acceleration too. So notice a positive angular velocity means that the object is rotating counterclockwise. And now angular acceleration. Remember that before we defined the acceleration to be the velocity at a later instant minus velocity at an earlier instant divided by the elapsed time. And it's gonna follow that same form here. So similarly, the angular acceleration is equal to the angular velocity at the later instant minus angular velocity at the earlier instant divided by the elapsed time. And anyone remember, so why for acceleration don't I need to think of first the average and then do an approximation as time gets small? Anyone remember why I didn't do that for acceleration? That's right. So you would have to do that in general, but the problems that we dealt with had constant acceleration, and it's the same thing here. We're only going to deal with constant angular acceleration, and so that's why we don't need the approximation idea. SI units. In the numerator, what are the units? Yep, radians per second, and in the denominator is seconds. So now we have radians per second squared. Or, again, if you think of radians as not really being there, then it's just 1 over second squared. And here's something, so notice the relationship between direction of velocity and direction of acceleration. You know, we've talked about this a million different times. If velocity and acceleration are in the same direction, it means a particle is speeding up. If they're in opposite directions, it means they're slowing down. You have a similar relationship with these angular quantities too. So if the angular velocity and angular acceleration have the same sign, then the object's rotation is speeding up. And if they have opposite signs, the object's rotation is slowing down. Any questions about any of this so far? Okay, so now there are two equations that we're going to use to relate angular quantities of an object to translational quantities of a point on the object. So these relate the angular quantity of the whole body to the translational quantity of a chosen point on the body. So there's one relating angular velocity to translational velocity, and that says that the magnitude of the velocity, the speed, is equal to the absolute value of the angular velocity times r. And this r is the distance from the pivot point to the chosen point. And then the acceleration one says the magnitude of not the entire acceleration, but the tangential acceleration is equal to the angular acceleration times r, all absolute value. And that r means the same thing. Okay, so these are going to be important. And let me do an example problem. So let's say we have like a wheel of fortune type wheel. It's rotating about, so the pivot is the center, okay? And let's say that we're interested in the translational quantities of this point A. That's a distance of 0.3 meters from the pivot point. And let's say that the wheel's angular velocity is positive 10 radians per second. And its angular acceleration is negative 5 radians per second squared. And we want to calculate two things. First, what's the velocity vector of the point A? And second, what's the total acceleration vector of the point A? All right, so for the velocity vector, oh, I forgot to make an important note here for these. Squeeze this in where you can. Sorry about the mess. But you have to notice that for these two equations that relate the translational quantities to the rotational quantities, notice that they don't give you any directional information. That's what all the absolute values are saying. Okay, they're only giving you magnitudes. So no directional information is given by these equations. The directional information all has to come from you thinking about the circular motion intuitively based on what you know from circular motion. So the directions have to come from your intuition about circular motion. Okay, so before I go on to calculations here, let's think about what the circular motion of this point A tells us. Okay, this is one reason why we went through all those exercises where we were doing basically this. So the angular velocity is positive 10. So which way is it rotating? Clockwise or counterclockwise? Counterclockwise. And so this point A is following a circular path like this, right? So what direction is the velocity vector? This thing is definitely moving along this circular path, so its velocity at this point is either up or down. It's down because this is moving counterclockwise. The angular acceleration and the angular velocity are opposite signs. So is the rotation speeding up or slowing down? Slowing down, so which direction should the tangential acceleration be? Yep. And now that's not all. This point is in circular motion, so what other acceleration part are we missing so far? There's centripetal also, and that's going towards the center of the circle. Okay, so now we have all the directions. These equations will give us the magnitudes. So we can combine those to get vectors. And so the magnitude of the velocity is equal to 10 radians per second times 0.3. So you get 3 meters per second. And so what does that tell us about the velocity vector? What are the components of the velocity vector? It's in the negative y direction, so 0, -3 meters per second. And then for the tangential acceleration, that's equal to the absolute value of -5 times 0.3. That's the same thing as 5 times 0.3. So you get 1.5 meters per second squared. And so what are the components of the tangential acceleration? Yep, 0, positive 1.5 meters per second squared. To get the total acceleration, we have to figure out the centripetal. The magnitude of the centripetal acceleration is the speed squared over the radius, which is 3 squared over 0.3. So 30 meters per second squared. And what are the components of the centripetal acceleration? Yeah, 30x, 0y. And so to get the total acceleration vector, it's 30, 0, plus 0, 1.5. So you get 30 meters per second squared, 1.5 meters per second squared. And then if you knew the mass of that point, you could use this acceleration and Newton's second law to figure out what force the surroundings were applying to this object to keep it there, which is the kind of analysis you would have to do if you're engineering something. You know, if you knew there was going to be some kind of camera there or something and you needed to measure those forces, that's the kind of approach that you would take. Any questions about that example? Now, the last cool thing about rotational kinematics, before I go on to rotational kinetics, and that is those 3 or 6, depending on 1D or 2D equations that we used for constant acceleration. Those, the analogs of those all apply for rotational motions. So omega F is equal to omega initial plus alpha TF. Theta F is equal to theta initial plus omega initial TF plus 1/2 alpha TF squared. And 2 alpha times the quantity theta F minus theta initial is equal to omega F squared minus omega initial squared. Okay. Yes. Okay, so now angular kinetics, or rotational kinetics. I guess I've been calling it rotational. So. What we're doing is working towards a rotational version of Newton's second law. I always just end up calling that Rn2L. Working toward. And so before we can get there, I have to define the 2 rotational quantities that I haven't defined yet. We've talked about angular acceleration, but we still need to define the moment, and we need to define the moment of inertia. So I'm going to start by defining the moment of a force about a point. And you can think of this as a measure of how strongly a force causes rotation of, let's say, of the chosen body. Okay, so here's the definition. If you just, so this is some random chosen body. And say that this body pivots around this point A. And let's take, like, choose some point P and draw a line between A and P. Okay. Then if the force vector F is perpendicular to the line between A and P, then the moment about that point A that's produced by that force, and this is an absolute value again, is equal to the absolute value of the force times d. I should have put this on the next page. I'm going to. So the absolute value of the moment is equal to the absolute value of the force times d, where F is the magnitude of the force and d is the distance between those points A and P. Where A is the pivot point and P is where the force is applied. Okay, so if I go back to this picture, there are infinitely many possible directions that this force could go, right? But I'm saying if it just happens, if you're so lucky that out of those infinitely many possibilities, that force is perpendicular to this line, so it's either going this way or this way. Let's say it's going like this. Then you calculate the moment like this. Okay? That doesn't give the direction. So notice the sign of MA is positive if MA causes a counterclockwise rotation and the sign of MA is negative if MA causes a clockwise rotation. All right, so what this says is, intuitively, imagine that you're trying to turn this bolt with a wrench. If you're trying to, if you know that you can apply a force of, say, 500 newtons, that's the strongest you are, you know? You can't do anything about that in the short term. Where do you want to apply that force in order to get the maximum rotation? Do you want to apply it here, or here, or here, or here? And you know from experience that you don't want these. You want to apply your force as far from the pivot point as you can. That's going to, without increasing the force at all, that's going to make your moment bigger, and it's going to be more likely to cause a rotation. So that's the idea of a moment. And you also know from experience, well, I don't know, maybe, you definitely have the intuition that if you tried applying that 500 Newton force straight down on the bolt, you could increase that force to 1,000,000 newtons, and you're still not going to get that to rotate. You would eventually just shear the bolt right off, but it would never rotate. You need that distance from the pivot point in order to get a rotation. Okay. But so far, like, there's sort of a big gap in that definition of the moment because, like I said, there's infinitely many directions the force can go. How many times are you going to get lucky enough to have it be exactly perpendicular to that line? Okay. So great, but what about when the force vector isn't perpendicular to the line between A and P? And it turns out that without changing the problem, without changing the behavior, you can always assume that the force acts anywhere along its line of action. And here's the idea of the line of action. So if you have an object and a force is applied here, okay, without changing the behavior of the system, you can move that force mathematically anywhere along this dotted line. It's a line that's parallel to the force and goes through the point where the force actually applies. Okay, even up here, you can even move the force to this theoretical point that's not even on the real body. But mathematically, you just sort of pretend like that body still has, is still going on way out there. So this is equivalent to this. If that's a force F, that's a force F. Okay? So you can move that force wherever you want as long as you keep it on that line of action. So what you do is you move the force along its line of action until the force vector is perpendicular to the line between A and P. So for example, if you had an object like this and a force applied in that top left corner, and say the pivot point A is there, and let's say this length is 2 meters and this length is 1 meter. Well, right now, the line between A and P is not perpendicular to the force, right? So here's the line of action of the force. It extends all the way to the right and all the way to the left, and you can move that force anywhere along that line of action. So where do we want to move that point P to? Yeah, we want to move P to right here. And so then the line between A and P is this. It's now perpendicular to the force. The absolute value of the moment is equal to, oh, this is 1 meter. The absolute value of the moment is equal to that distance, 0.5, times the magnitude of the force, 20. And so you get 10 Newton meters. And then what direction of rotation would that force cause? A clockwise or a counterclockwise rotation? Yep, it would cause a clockwise rotation. So MA is equal to negative 10 Newton meters. And the SI units for moment are Newton meters. We've seen a quantity with units of Newton meters already. Do you remember what that is? That might be right, I didn't hear. But let's say that it is. Energy. So energy has units of, there's a couple ways you can express it, but one of them is Newton times meter. With energy, we called it a joule. So we could call this a joule, but we don't, just so that we don't mix up energy units with moment units, because even though they have the same units, they're not the same thing. Okay? So don't call this joule, even though you could. Any questions about moments? Okay, the last thing I need to define is the moment of inertia. So the mass moment of inertia, and the mass moment of inertia, just like the moment does, has a point associated with it. It's not defined until you choose that point, so I'm going to put this in parentheses, but most people just call it, when people are talking about it, they just call it the mass moment of inertia, or even just the moment of inertia. It's a positive quantity that's large if an object is hard to rotate and small if an object is easy to rotate. So, for example, if that's a gymnast, this is the position that it's the easiest to do flips in. That has a small moment of inertia. This is the position that's hardest to do flips in. So that has a large moment of inertia. And it's a measure of how much mass is distributed far from the pivot point. I think we're just going to have to do rotational kinematics on the test. We still have some stuff to cover. So let's just, okay, exam 5 is not going to have any rotational kinetics. I'll put this on D2L too. Okay, so I guess that means we're done. Any questions about where this ended, or 20%? The other ones are 15%, so it's not that much different than the other exams.
So what we have up to now is 80% of our grade.
Yes, except you probably haven't turned in the second problem set.
Oh, right.
And you haven't done the last lecture quiz, and you haven't seen your score on the makeup exams. So there still could be a lot undetermined if you did a makeup exam, especially, you know.
About 75.
Well, if you took a makeup exam, then it would be still 20% plus 15% plus 5 more for the quizzes plus 5 more for the, so it would be close to 50% still. It would be more like 30 or so, 35% if you didn't do a makeup exam.
I had a question.
Yeah.
The mass moment of inertia, is that kind of like torque? Or?
That is, the moment is the torque. Moment is torque. Mass moment of inertia is it has to do with the object that you're trying to get rotating. So, like,
How the mass is distributed?
yeah, so if you had, how much do you think a big 2x4 weighs? Like, let's say 20 pounds?
Well, I said a few pounds, I don't know.
Okay, let's say 20 pounds. And then imagine you had a disc or like a shot put weighs about 20 pounds. So imagine a shot put like this. Which one would, just picture which one would be harder to get rotating like on ice? The shot put or the 2x4? They'd be equally hard to get accelerating, but the shot put would be easy to get rotating. The 2x4 would take more work to get rotating. That's because even though they have the same mass, the 2x4 has a bigger moment of inertia.
There's more to it than that, huh?
It just has to do with,
There's something going on there with the fact that
it's how, even though they have the same mass, the 2x4's mass is spread out farther from its pivot point. And that's why it has a bigger moment of inertia.